Hi everybody, I'm Guillaume and I'm a PhD student at the Department of Physical Geography in Stockholm University. And I'm going to present you my research about investigating land sea and hydroclimatic linkages for coastal eutrophication management in the Baltic Sea. And this is related to my PhD thesis, so it is a summary, so I will not go into details in the methods. But so as you know, coastal eutrophication is a major issue that affects more than 900 coastal and marine areas worldwide. And it's also a problem in the Baltic Sea, circled in blue here, where most of the open sea water and coastal water are still suffering from that issue, but with some also recent coastal improvement in the recent year. And coastal eutrophication is most often due to an increase in anthropogenic nutrient load to the water body that then fuels the growth of algae and increases organic matter production and further change the biogeochemical processes associated, and then has consequences for the whole food web by, for example, increasing hypoxic condition and then decrease the biomass of benthic fauna. But in addition to this anthropogenic nutrient load, there are also other factors from the open sea, the climatic drivers or other stressors that might have an influence. And this is then the aim of my thesis, that aims to investigate how combined hydroclimatic, land-based, and coastal drivers can affect coastal eutrophication, and also how their effects propagate through the land-coast-sea continuum. And that has been done through three objectives. The objective A is to focus on the influence of the land catchment, coastal and open sea interaction, and see what effect they have on coastal eutrophication and also on its management. Then the second objective B are the hydroclimatic drivers and conditions that may have influence on coastal eutrophication. And finally, we also wanted to study how the research literature has handled the coastal eutrophication complexity in the Baltic Sea system. And so here you have a map of the Baltic Sea system, with in green the land catchment area, in light purple the open sea, and in dark purple the Baltic Sea coast, that is then the whole focus area for the objective C. Then the analysis of drivers has been done on the Swedish coast, outlined in yellow, and through data analysis. And the first objective has been mostly focusing on the Himmerfjärden Bay, circled in red, which is a small bay south of Stockholm. And so the analysis of land-coast sea interaction has been done through a water quality modeling approach. That is a relatively simple model that describes phytoplankton growth depending on nutrient concentration as well as nutrient in the sediments. And this model is then applied both on the Baltic Sea scale and on the coastal scale on the marine basins and the coastal basins. And results from the marine basins are then used as boundary conditions for the coastal model. And it has been run with three or different scenarios. So one baseline scenario that assumes no reduction in loads, in nutrient loads. A land-based scenario that assumes some reduction in river and point source loads. A sea-based scenario that considers that the open sea boundary condition reach a good ecological status, and finally a combined scenario. And here we can so this figure presents the distribution of percentage of reduction in the DIN, so which is a disolved organic nitrogen, disolved organic phosphorus, and chlorophyll A compared with the baseline scenario, to see the influence of the different land-based, sea-based, and combined scenario. And we can see that the land-based scenario has a strong effect, has a strong effect on the DIN component, and much lower effect on average on the DIP and chlorophyll A, but still allows significant reduction in some area of the bay. The sea-based scenario, on the other hand, has stronger effect for the DIP component and the chlorophyll A component, and even can lead to increases in DIN concentration due to decrease of denatrification. And we can see then that the combined scenario leads to the best result across both DIN, DIP, and chlorophyll A. And for the second objective, it was also due to the fact that in the Swedish coast, we can observe both decreasing and increasing trends of eutrophication in different coastal areas. And so we wanted to investigate from a data-driven perspective how the trends in variables such as coastal summer chlorophyll A and nutrient concentration are affected by some trends in drivers, and we selected driver acting over the land catchment, driver acting over the coastal or marine basins such as sea ice and wind speed, and open sea driver that are then nutrient concentration in the open sea. And we have then correlated these trends between drivers and variables as exemplified in here. So we first calculated the trends for the variables here, temporal trends and temporal trends for the drivers, and then correlated those trends within the period 1990 to 2020. And this then shows the amount of spatial variability in variable trend that is explained by the spatial variability in driver trends. And we've done that both considering all coastal basins that have enough data, but also dividing between more and less isolated coastal basin, depending on the water flow, water exchange with the open sea. And so this table here represents then the correlation coefficient between trends in drivers, so on the left, and trends in variables. And so for the land catchment and basin drivers, the variable used here is summer chlorophyll A, and we also did that for the open sea driver, considering correlation between summer chlorophyll A or dissolved inorganic nitrogen with the respective variable concentration in the different part of the, so for the more isolated, less isolated coastal basins. And looking at the land-based driver, we can see that the main influence comes from the load of dissolved inorganic nitrogen that influence all the coastal basin. For the open sea condition, then this influence is more on the concentration and precipitation, or correlates more with the concentration and precipitation. Looking at the basin driver, we can see that the last days of the sea ice condition are the one that appear to have the strongest or that have the strongest correlation with trends in chlorophyll A. So they could represent either hydroclimatic aggregation that are relevant for coastal eutrophication, or but they can also have direct influence on the spring bloom that may also then influence further the summer concentration of chlorophyll A. And the marine basin is then mostly correlated with water salinity and wind speed. And looking at the open sea drivers, we can see that the summer chlorophyll A condition in the open sea are very well or are well correlated with the one in the less isolated, but not so much considering the more isolated coastal basin. However, for dissolved inorganic phosphorus, we can see that this correlation is good over all the coastal classes. And so this indicates that the coastal eutrophication is influenced by land-based driver, but also by hydroclimatic condition and open sea condition as well. And finally, looking at the how coastal eutrophication in the Baltic Sea has considered the research on coastal eutrophication in the Baltic Sea has considered the different system interlinkages. We performed a screening review from papers that have a focus on Baltic coastal eutrophication. And we classify them into different topic supercategories that are whether they mostly focus on investigating drivers, investigating impacts or characterizing eutrophication condition, but also how do they link with land-based and open sea condition, whether they just mention their influence or actually investigate and quantify them, and which coastal system components do they consider in terms of coastal functions, natural driver, anthropogenic driver, and management. And this graph here shows the circles are proportional to or depend on the research effort in each of those categories. So the percentage of paper that is classified in one of these categories. And we can see that more papers are focusing on impacts and drivers of eutrophication and on characterizing it. Moving to the links with land coast sea. So many papers do mention the links and the influence of land and open sea influence, but much fewer papers investigated those links, and mostly in terms of driver studies. Then the main system components are all relatively well investigated, but looking at specific driver, we can see that, for example, legacy sources or CIs, as well as some coastal function and management solution on the coastal scale are generally under-investigated. And so to conclude, from objective A, we can see that open sea water quality improvement can lead to large substantial improvement in coastal water areas, while for the bay we investigated with relatively small river, the land-based nutrient reduction were more localized, especially for DIP and chlorophyll A, with also a larger spread for nitrogen. And so that reducing coastal eutrophication would require both reducing land-based loads, but also improving open sea conditions. In terms of driver, coastal water appears to be a melting pot of driver and condition from different parts of the system, both from land, the open sea, and climate. And we can also see that the literature generally considers quite well the different system components of driver, coastal function, and management, but that some specific coastal functions and drivers are under-investigated, and also the coastal management solutions, which also may be efficient against legacy sources. And so this is a quite important research gap. And finally, for managing coastal eutrophication, there needs to be a consideration of this interaction with the different, the regional and local scale and driver, but also with the impacts and feedbacks with those impacts. So thank you for listening.
Thank you, Guillaume.